Feel the warmth for a moment. Even if you're inside, even if it's night, you know what it feels like. That particular quality of sunlight on your face, or your arm on a clear afternoon. The way it settles into you, the way it has a weight to it, almost. A pressure that you can feel, but not quite measure. Not the sharp heat of a fire nearby, not the diffuse warmth of a heated room, but something more specific, more directional, more ancient in feel. The warmth of a clear day outdoors, the kind that makes you stop walking and turn your face upward for a moment, the kind that has been doing exactly that to human beings for all of human history. That warmth has been falling on human faces for as long as there have been human faces. For 200,000 years of our species, and hundreds of millions of years before that for our ancestors, that warmth has been there. Every morning, every clear afternoon, every time the clouds parted and the angle of the sun was right, that warmth, constant, reliable, the single most dependable thing in all of human experience. It comes from a star, not just any star, the closest one. A star so close that it appears as a disk in the sky rather than a point of light, close enough that its light reaches you in just over 8 minutes, close enough that you can feel it on your skin, 93 million miles away, and yet close enough to warm you. That is an almost incomprehensible fact when you hold it properly. The nearest other star is about 25 trillion miles away. We're close to our star. Cosmically, absurdly close. If all the other stars were as close as the nearest one, they would each be about 80 times further away than the sun. We are extraordinarily fortunate in our proximity to our star. Think about who else has felt that warmth. Every child who has sat in the sun on a school day, grateful for the warmth on their back. Every farmer watching the sky, calculating whether there'd be enough sun for the crops. Every traveler making their way across a mountain pass, feeling the sun come out from behind clouds and finding their spirits lift, involuntarily, the way spirits do in sunlight. Every prisoner who was allowed an hour in the courtyard, every old person sitting by a window on a winter afternoon with the low-angle sun full on their face, every couple lying on a beach, every soldier resting before a battle, every child of every era, turning their face upward on a spring day and squinting into the light. The same sun, the same light, the same fusion reactions in the same core, producing the same photons, sending them on the same 8-minute journey. 4.5 billion years of days, every one of them powered by the same source, every one of them providing the same warmth to whatever was living on the surface of this planet at the time. The sun, the thing that makes days and drives seasons and powers almost every living thing on this planet, directly or indirectly, the thing that plants are reaching for, that animals navigate by, that ancient peoples worshipped, that children are told never to look at directly, the thing that has been there, reliably, every single day of your life, and every single day of every human life that has ever been lived. Tonight, we're going to talk about it, about what it actually is, and what's actually happening inside it, and how we came to understand it, and what it's made of, and how long it will last, and what will happen when it's done, slowly, gently, without rushing anything. If you drift off somewhere along the way, that's perfectly fine. The sun will rise again in the morning. It's been doing that for 4.5 billion years, and it has another 5 billion or so left in it. There's no urgency. But if you stay with me, I think you'll find that the story of how the sun works is one of the most beautiful and profound things that physics has ever uncovered. It's a story about fire that isn't fire, about a process so different from anything in our daily experience that it took centuries of careful science to understand, and that even today has aspects that still puzzle the best solar physicists in the world. Let's begin at the beginning, with the most basic question: what is the sun? The sun is a star. This sounds obvious now, but it was not obvious for most of human history. For almost all of human civilization, the sun was simply the sun, a special thing, the giver of light and warmth, something different in kind from the tiny points of light that appeared at night. The idea that the sun might be the same type of object as the stars, just much closer, took a remarkably long time to arrive and was seriously controversial even after it was first proposed. The ancient Greeks had various ideas about the sun. Anaxagoras, in the 5th century BC, suggested that the sun was a mass of incandescent rock, perhaps as large as the Peloponnese Peninsula. He was mocked for this. His contemporaries thought the idea that the sun could be a physical object made of ordinary matter was absurd. They prosecuted him for impiety. He spent his final years in exile. The sun was divine, or at least something more than mere matter, and to suggest otherwise was religiously offensive. Aristarchus of Samos, in the 3rd century BC, proposed that the Earth orbited the sun rather than vice versa. He was largely ignored. The geocentric model, with Earth at the center of the cosmos, was more intuitively appealing and more consistent with common sense, which told you that if you were moving, you would feel it. Aristarchus was nearly 2,000 years ahead of his time. The idea that the stars were distant suns was proposed more clearly by various thinkers over the centuries, gaining real traction in the 16th and 17th centuries. Giordano Bruno, the Italian philosopher, embraced the idea enthusiastically and extended it to argue that the universe was infinite and contained many worlds around many suns. He was burned at the stake in 1600, though his cosmological views were only part of the complex of charges against him. The astronomer Christiaan Huygens, in the late 17th century, made careful comparisons between the sun's brightness and the brightness of stars, trying to estimate how far away the stars must be if they were comparable to the sun in intrinsic brightness. He concluded they must be at distances so vast as to be almost beyond imagination. He was essentially right. Galileo's invention of the astronomical telescope, or his adaptation of existing Dutch designs for astronomical use, in 1609, transformed solar observation. Through his telescope, Galileo could see sunspots clearly. He tracked them across the face of the sun over days and weeks, observing that they moved in a consistent way that showed the sun was rotating. He correctly concluded that sunspots were features on the sun's surface, not objects passing in front of it, as some had suggested. This seemingly obvious conclusion was actually contested at the time. The Jesuit astronomer Christoph Scheiner, in an extensive and rather bitter priority dispute with Galileo, initially argued that sunspots were small planetary bodies orbiting close to the sun. Eventually, the debate was settled in Galileo's favor, but it's a reminder of how contentious basic observations about the sun could be in the early 17th century. Before telescopes, sunspots were occasionally noticed by observers looking at the sun through fog, thick clouds, or smoke that reduced its brightness enough to make direct observation possible without damage to the eye. Chinese astronomical records include descriptions of sunspots going back to at least 28 BC, often described as black spots or dark shapes on the sun. Arab astronomers also recorded them. In Europe, large sunspots were occasionally noted by medieval astronomers, But systematic study of sunspots was only possible after the telescope. In the centuries after Galileo, solar observation became increasingly precise. By the early 19th century, astronomers were tracking sunspots methodically, and by 1843, the German amateur astronomer Heinrich Schwabe, who had been hoping to discover a planet inside Mercury's orbit, had instead noticed that sunspot numbers varied in a regular cycle of about 11 years. His discovery of the solar cycle, which he had been quietly accumulating evidence for over 17 years of patient daily observation, was initially not widely noticed. But Alexander von Humboldt, the great naturalist and scientific popularizer, included Schwabe's result in his comprehensive work Cosmos in 1851, and from then on, it was recognized as a fundamental discovery. The 11-year solar cycle is now known to be only the visible surface of a much longer cycle. The magnetic polarity of the Sun reverses with each 11-year cycle, so that the complete magnetic cycle is about 22 years. The overall patterns of solar activity also vary on longer timescales, with the Maunder Minimum and similar grand minima being features of cycles centuries long. The causes of these longer-term variations are still not fully understood, but the basic 11-year cycle is reliably regular and has been used for planning everything from radio communications to satellite operations. By the 19th century, the stellar nature of the Sun was well established. It was a star. The question was, what kind of star? And more importantly, what made it shine? This last question was deeply puzzling. The Sun emits an extraordinary amount of energy. By the mid-19th century, physicists could calculate the total power output of the Sun from its brightness and distance. The answer was about 3.8 times 10 to the 26th watts. That's 386 trillion watts. Every second, the Sun releases more energy than all of humanity has produced in the entire history of civilization. Every second. The question was, where does that energy come from? What is burning? The most obvious hypothesis was that the Sun was literally burning. Combustion, the way wood burns or coal burns. But the problem with this was simple and devastating. If the Sun were made of the best combustible material known, coal, pure coal, burning in air at the most efficient possible rate, it would burn out in about 5,000 years. That was already known by the mid-19th century to be far too short. Geological evidence was showing that the Earth was millions or hundreds of millions of years old. The Sun had to have been shining for at least that long. Chemical combustion was completely inadequate. A more promising idea was gravitational contraction, proposed by the German physicist Hermann von Helmholtz in 1854, and independently by the English physicist Lord Kelvin. The idea was that the Sun was slowly contracting under its own gravity, and as it contracted, gravitational potential energy was converted to heat and light. The numbers were much better than combustion. A contracting Sun could shine for about 25 million years before running out of gravitational energy. That seemed like a lot, but it wasn't enough. Hermann von Helmholtz was one of the great scientific minds of the 19th century. He trained as a physician, worked as a military surgeon, and in his spare time did physics that transformed several fields. He proved mathematically that energy was conserved in all processes, the first full statement of what we now call the first law of thermodynamics. He studied optics and invented the ophthalmoscope, the instrument doctors use to look inside the eye, which he developed in 1851 and which is still in use today in essentially the same form. He worked on hydrodynamics, electromagnetism, acoustics, and the physiology of perception. He was, in the breadth of his contributions, one of the last universal scientists. William Thomson, who became Lord Kelvin when he was elevated to the peerage in 1892, was a Scottish-Irish physicist who made fundamental contributions to thermodynamics, the theory of electricity and magnetism, and the laying of the first successful transatlantic telegraph cable in 1866. The temperature scale named after him, the Kelvin scale, starts at absolute zero, the coldest possible temperature, and is used universally in science. He was a Victorian polymath of the highest order. Kelvin was also one of the most famously wrong about the age of the Earth. Using what he believed was sound physics, the rate at which a initially molten Earth would cool, he calculated in 1862 that the Earth was between 20 and 400 million years old, with his preferred estimate being about 25 million years. When geologists and biologists protested that this wasn't enough time for the geological and biological record, Kelvin was dismissive. He was confident in his physics. He was wrong. He didn't know about radioactive heating, the heat produced by the decay of radioactive elements in Earth's interior, which keeps Earth warmer than it would be if it were simply cooling. He didn't know about nuclear fusion, which powers the sun. He was working with incomplete physics. His errors were not mathematical errors or reasoning errors. They were errors of ignorance, because the relevant physics hadn't been discovered yet. This is worth remembering. Kelvin was one of the greatest physicists of his era, careful and rigorous, and he still got fundamental things wrong, because the knowledge he needed didn't exist. Science is always working with incomplete information. The best we can do is be honest about the limits of what we know and remain open to revision. Darwin's theory of evolution, published in 1859, and the subsequent geological evidence for the age of the Earth were pushing the required age of the Sun well beyond 25 million years. By the late 19th century, estimates of Earth's age based on sedimentation rates, the cooling of the Earth, and other geological methods were pointing to hundreds of millions of years at minimum. The sun had to have been shining for at least that long. Gravitational contraction wasn't enough either. The answer was not found until the 20th century, and it required a revolution in our understanding of the atom. The key discovery came from two directions. The first was Einstein's special theory of relativity in 1905, specifically the equation E equals mc squared, which showed that mass and energy were equivalent. A small amount of mass was equivalent to an enormous amount of energy, because the conversion factor was the speed of light squared, an enormous number. The second was the gradual unraveling of atomic structure, culminating in the discovery of the atomic nucleus by Ernest Rutherford in 1911, and the subsequent development of nuclear physics through the 1910s, 1920s, and 1930s. Ernest Rutherford is worth a moment's attention here, because his discovery was so fundamental. Rutherford was a New Zealand-born physicist working in Britain, a man of extraordinary experimental ingenuity, and a personality so forceful that his colleagues joked that wherever Rutherford sat was the head of the table. In 1909, working with his students Hans Geiger and Ernest Marsden at the University of Manchester, Rutherford directed a beam of alpha particles, which are helium nuclei, at a thin sheet of gold foil. The expectation, based on the then current model of the atom as a diffuse ball of positive charge, with electrons scattered through it like raisins in a pudding, was that the alpha particles would pass through the foil with only slight deflections. What they found instead was that most alpha particles did pass straight through, but a small fraction were deflected at large angles. A tiny fraction bounced almost straight back. Rutherford later said this was as astonishing as if you fired artillery shells at tissue paper and they came back and hit you. The only explanation was that the positive charge of the atom was not spread throughout a diffuse cloud, but was concentrated in a tiny, dense nucleus at the center, with the electrons orbiting at relatively large distances. The atom was mostly empty space, with almost all its mass concentrated in a minuscule core. This nuclear atom, Rutherford's model, transformed physics. It led to quantum mechanics, to the understanding of atomic spectra, and eventually to the study of nuclear reactions themselves. What could happen if you hit a nucleus with another particle? By the 1930s, physicists understood that nuclei contained protons and neutrons, that the strong nuclear force held them together, and that nuclear reactions could release or require enormous amounts of energy, far beyond anything possible through chemistry. The question of stellar energy had a candidate mechanism. The theory was worked out in detail in the 1930s by several physicists, most notably Hans Bethe, a German-American physicist working at Cornell University. Bethe is one of the most remarkable figures in 20th century physics, combining extraordinary mathematical power with unusual breadth and an almost systematic approach to problem solving. Hans Bethe was born in Strasbourg in 1906, then part of Germany. His father was a physiologist. His mother was Jewish, which would eventually force him to leave Germany. He showed exceptional mathematical ability from childhood. He studied physics at Frankfurt and Munich, working under Arnold Sommerfeld, one of the great teachers in the history of physics. He received his doctorate in 1928 at the age of 22. In the early 1930s, he held positions at several German universities and was building an extraordinary reputation in theoretical physics. Then the Nazis came to power in January 1933. Bethe, because of his mother's Jewish heritage, was immediately dismissed from his position. He spent a couple of years in England, at Manchester and Bristol, before moving permanently to Cornell University in the United States in 1935. At Cornell, Bethe became one of the most productive theoretical physicists in the world. He worked on nuclear physics, atomic physics, solid-state physics, and quantum electrodynamics. He was unusually organized and systematic in his work, with a habit of working through all the possibilities methodically rather than jumping to the most likely answer. This approach served him well in the stellar energy problem. In 1938, George Gamow and Edward Teller organized a conference in Washington, D.C., bringing together nuclear physicists and astrophysicists to discuss the problem of energy generation in stars. Bethe attended, and within a few months of the conference, had worked out the main mechanisms in detail. He showed that in stars like the Sun, the dominant process was the proton-proton chain we've already described. In more massive, hotter stars, a different set of reactions called the CNO cycle, using carbon, nitrogen, and oxygen as catalysts, was more important. He published his results in 1938 and 1939 in papers that are still considered classics of theoretical astrophysics. The Nobel Prize came much later, in 1967. Bethe went on to lead the theoretical division of the Manhattan Project at Los Alamos from 1943 to 1945. Applying his knowledge of nuclear physics to the design of the atomic bomb. After the war, he became an outspoken advocate for nuclear arms control, working for decades to limit the proliferation of nuclear weapons, one of the physicists who most clearly recognized the moral implications of what they had created and worked most persistently to contain the danger. He was still publishing significant physics papers in his 90s. He died in 2005 at the age of 98. His career spanned from the early quantum mechanics of the 1920s to the particle physics and astrophysics of the early 21st century. He was one of the last connections to the founding generation of modern physics, and one of the most complete physicists of his era. His work on stellar energy generation was important not just for explaining where the sun gets its energy, but for establishing the broader field of nuclear astrophysics, the study of how nuclear processes in stars determine the properties of stars and create the elements that fill the periodic table. Every element heavier than hydrogen and helium was made in a stellar nuclear furnace, through processes that Bethe and his colleagues worked out in the mid-20th century. The iron in your blood was made in a massive star that lived and died before the solar system formed. The carbon in your body was made in stellar cores through the triple alpha process that we described when we talked about neutron stars. The gold and platinum, as we've discussed, were made in neutron star mergers. All of chemistry, all of biology, all of the material world around you is the product of stellar nuclear physics, understood first through the patient work of people like Hans Bethe. Once it was understood that atomic nuclei contained enormous stores of energy that could, in principle, be released by rearranging them, the source of stellar energy became clear. The sun was powered by nuclear fusion, the combining of lighter atomic nuclei into heavier ones with the release of energy. But we're getting ahead of ourselves. Let me slow down and walk through what the sun actually is before we talk about how it burns. The sun is a ball of plasma. Plasma is the fourth state of matter, the one that doesn't get taught in most school science classes, which focus on solid, liquid, and gas. Plasma is matter so hot that the atoms that make it up have lost their electrons. The electrons have been stripped away from the nuclei by the violence of thermal collisions. Instead of neutral atoms, you have a sea of positively charged nuclei and negatively charged electrons, moving independently at high velocities, all mixed together in a soup of electrical charge. Plasma behaves differently from ordinary gas because all these charged particles interact with each other electromagnetically, creating complex flows and structures that neutral gas doesn't have. The entire sun is plasma. The surface of the sun, the part we see from Earth, is plasma at a temperature of about 5,500 degrees Celsius. The interior is plasma at temperatures ranging up to about 15 million degrees Celsius at the very center, the core, where the nuclear fusion takes place, and the outer atmosphere of the sun, the corona, which we'll talk about in detail later, is plasma at temperatures of more than 1,000,000 degrees Celsius, a strange and still not fully understood inversion that has puzzled solar physicists for decades. The sun is not solid anywhere. There is no solid surface to stand on, no hard boundary between inside and outside. The sun just gets denser and hotter as you go in toward the center, with the plasma becoming progressively more compressed until you reach the core. Let me give you some numbers to hold the scale in your mind. The sun's diameter is about 1.4 million kilometers. Earth's diameter is about 12,700 kilometers. You could line up about 109 Earths across the diameter of the sun. If the sun were hollow, you could fit about 1,300,000 Earths inside it. The sun contains about 99.8% of all the mass in the solar system. Everything else, the 8 planets, all the moons, all the asteroids and comets and dwarf planets, all of it combined is the remaining 0.2%. The sun is not just the center of the solar system. It is, in terms of mass, almost the entire solar system. The sun's mass is about 2 times 10 to the 30th kilograms. That's 2 billion trillion kilograms. Written out as a number, it has 30 zeros after the 2. It's not a number that has any intuitive meaning. You cannot build an intuition for it. You can only note that it's very large, and that gravity has squeezed all of it into a sphere 1.4 million kilometers across, and that the conditions this creates in the center are extreme enough to make nuclear fusion happen. Let's talk about that core. The core of the Sun occupies roughly the innermost 20 to 25% of the Sun's radius, a sphere about 300,000 kilometers across. This is not very large by solar standards, but it's where almost all of the Sun's energy is produced. The temperature in the core is about 15 million degrees Celsius. The pressure is about 250 billion times Earth's atmospheric pressure. The density is about 150 times the density of water, which is denser than any ordinary metal you can think of, though this dense material is plasma, not solid metal. Under these conditions of extreme temperature, pressure, and density, nuclear reactions happen. Specifically, a chain of reactions called the proton-proton chain, which is the dominant fusion process in stars like the Sun. The proton-proton chain starts when two protons, two hydrogen nuclei, collide at extremely high velocity. Under normal conditions, two positively charged protons would repel each other before they could get close enough to fuse, because like charges repel. This repulsion, the Coulomb barrier, is what prevents hydrogen from spontaneously fusing at ordinary temperatures. But in the Sun's core, where the temperature is 15 million degrees, the protons are moving so fast that some of them, through a combination of thermal velocity and quantum tunneling, can overcome the Coulomb barrier and get close enough for the strong nuclear force to take over. The strong force is enormously powerful at very short ranges and easily overcomes the electromagnetic repulsion when two protons get close enough. When two protons fuse, they form a very unstable nucleus called a diproton, which has two protons and no neutrons. Almost immediately, in most cases, the diproton simply falls apart again. But occasionally, through a process involving the weak nuclear force, one of the protons converts to a neutron, emitting a positron and a neutrino in the process. This produces a deuterium nucleus, sometimes called heavy hydrogen, which has one proton and one neutron. This conversion step is the bottleneck of the whole process. It's extremely rare. On average, a given proton in the Sun's core waits about 9 billion years before successfully fusing with another proton to produce deuterium. That extreme rarity is actually what gives the Sun its stability. If the fusion happened more readily, the Sun would burn much faster. Once deuterium is produced, the next steps happen much more quickly. The deuterium nucleus fuses with another proton to produce a helium-3 nucleus, two protons and one neutron, releasing a gamma-ray photon. This step typically takes only a few seconds to a few minutes. Two helium-3 nuclei then collide and fuse, releasing two protons and producing one helium-4 nucleus, the most common and stable form of helium, with two protons and two neutrons. This step takes place over timescales of years to thousands of years. The net result of this whole chain, starting from 4 protons, one helium-4 nucleus, 2 positrons, 2 neutrinos, and several gamma-ray photons. The helium-4 nucleus has slightly less mass than the 4 protons that went into making it. The difference is about 0.7% of the original mass. That lost mass is converted to energy according to E equals mc squared. It doesn't sound like much, 0.7%. But remember that c squared is an enormous number. 0.7% of the mass converted to energy at c², gives an enormous amount of energy per fusion event. Every second, the sun converts about 4 million tons of mass into energy. 4 million tons. The sun is literally losing mass, 4 million tons per second, by converting that mass to energy through nuclear fusion. Over the sun's lifetime so far, it has lost a total mass of about 100 Earth masses to this energy conversion. That still leaves it with 1,000 Jupiter masses worth of hydrogen fuel. These numbers are staggering, and yet the sun burns so steadily, so consistently, so calmly, that from our perspective on Earth it seems utterly constant. The solar output doesn't flicker in any way that human civilization has ever noticed on the timescale of lifetimes. It just shines, every day, reliably, while secretly, quietly, converting 4 million tons per second of itself into pure energy. Every second, the sun converts about 4 million tons of mass into energy. 4 million tons. The sun is literally losing mass, 4 million tons per second, by converting that mass to energy through nuclear fusion. Over the sun's lifetime so far, it has lost a total mass of about 100 Earth masses to this energy conversion. That still leaves it with 1,000 Jupiter masses worth of hydrogen fuel. These numbers are staggering, and yet the sun burns so steadily, so consistently, so calmly, that from our perspective on Earth, it seems utterly constant. The solar output doesn't flicker in any way that human civilization has ever noticed on the timescale of lifetimes. It just shines. Every day, reliably, while secretly, quietly, converting 4 million tons per second of itself into pure energy. Before we talk about how that energy travels from the core to the surface, I want to tell you about one of the most remarkable scientific stories of the 20th century. The story of solar neutrinos and how a tank of cleaning fluid deep in a South Dakota mine helped us understand the sun. Remember how I mentioned that the proton-proton chain produces neutrinos? Each time a proton converts to a neutron in the first step of the chain, an electron neutrino is released. Neutrinos, as we've discussed in our antimatter conversation, are ghostly particles that interact only through the weak nuclear force and gravity. They're almost completely undetectable. Billions of them pass through your body every second from the sun, and they pass straight through you without noticing you're there. The sun is transparent to them. This means that unlike the photons, which take 100,000 years to escape the solar interior, neutrinos produced in the core escape almost instantly at nearly the speed of light. They carry direct information about what's happening right now in the sun's core. Detecting them would be like having a direct window into the center of the sun. In the 1960s, the physicist Raymond Davis Jr. built an extraordinary detector to try to catch solar neutrinos. He filled a tank with 100,000 gallons of perchloroethylene, a common dry cleaning fluid, and placed it about 1.5 miles underground in the Homestake gold mine in South Dakota. The underground location was to shield the detector from cosmic rays, which would produce false signals. Occasionally, a solar neutrino would interact with a chlorine atom in the perchloroethylene and convert it to argon. Every few weeks, Davis would flush the tank with helium gas to collect the argon atoms, count them, and determine how many neutrinos had been detected. The detection rate was far lower than Bethe's solar model predicted. Davis was detecting only about 1/3 of the expected number of neutrinos. This discrepancy, which became known as the solar neutrino problem, persisted for 30 years. Either Davis's experiment was wrong, or the solar models were wrong, or something was happening to the neutrinos on their way from the sun to Earth. The solution, when it finally came, was the third option. Something was happening to the neutrinos. They were transforming, oscillating between different flavors, as we discussed in our antimatter conversation. The sun produces electron neutrinos, but by the time they reach Earth, some of them have become muon neutrinos, or tau neutrinos, which Davis's experiment couldn't detect. When later experiments were built that could detect all three types of neutrinos, the total count matched the solar models perfectly. The solar models were right. The sun was producing exactly the number of neutrinos predicted. Raymond Davis Jr. and the Japanese physicist Masatoshi Koshiba, who led a separate neutrino detection project called Kamiokande in Japan, using a huge tank of water rather than dry cleaning fluid, shared the 2002 Nobel Prize in Physics for their neutrino detection work. Their experiments confirmed the theory of stellar energy production and simultaneously revealed the new physics of neutrino oscillations. The solar neutrino story is a wonderful example of how science works. An experiment found a discrepancy. The discrepancy drove 30 years of investigation. The resolution revealed not that the solar models were wrong, but that we had incomplete understanding of neutrinos. A problem that appeared to be about the sun turned out to be about fundamental particle physics, and both areas of knowledge advanced as a result. Now let me tell you about what happens to that energy after it's produced in the core, because the journey from the core to the surface of the sun is one of the most extraordinary passages in all of astrophysics. The gamma-ray photons released by fusion reactions in the core do not simply fly out through the sun and into space. The sun is far too dense for that. A photon produced in the core immediately encounters other particles, is absorbed, re-emitted, absorbed again, scattered, re-emitted again. The solar interior is so opaque that a photon, on average, takes about 100,000 years to work its way from the core to the surface. Let me say that again. The energy produced in the sun's core today, the energy being released right now from nuclear fusion, will not reach the surface for about 100,000 years. The sunlight warming your face right now on a clear day was actually produced in the sun's core 100,000 years ago, around the time early modern humans were expanding out of Africa. The path a photon takes through the solar interior is what physicists call a random walk, sometimes called a drunkard's walk. The photon moves a short distance, hits something, bounces in a random direction, moves a short distance, hits something again, bounces again, over and over. Because each bounce sends it in a random direction, the net progress outward is extremely slow. It's like trying to make your way across a crowded room where every time you take a step, someone randomly bumps you in a different direction. You might make progress on average, but it takes much longer than simply walking straight across. The region of the sun through which energy travels in this way, by radiation, by the absorption and re-emission of photons, is called the radiative zone. It extends from the core to about 70% of the sun's radius. In this zone, energy moves by radiation, by photons being passed from particle to particle in an enormously slow random walk. Above the radiative zone, in the outer 30% of the sun's radius, a different energy transport mechanism takes over: convection. In this region, the solar material is hot enough that it can rise, carry its thermal energy upward, cool near the surface, sink back down, and rise again. Just like water boiling in a pot on a stove, the hot material physically moves, carrying energy with it, far more efficiently than radiation could. The convection zone creates the roiling, bubbling surface appearance that the sun has when observed closely. The convective cells are called granules, and they're visible through telescopes as a pattern of bright centers, surrounded by darker edges, like the surface of a rice pudding, or the skin of an orange, or perhaps most vividly, like a pot of oatmeal on the verge of boiling. Each granule is a convective cell, perhaps 1,000 kilometers across, with hot plasma rising at its center and cooling plasma sinking at its edges. A granule lasts for perhaps 10 to 20 minutes before being replaced by new ones. The entire surface of the sun is covered in these granules, perhaps 2 million of them at any given time, each rising and falling in the ceaseless convective motion that carries energy from the radiative zone up to the surface. There are also larger convective structures, called supergranules, which are about 30,000 kilometers across and last for about a day or two. Supergranules were discovered in the 1950s and are still not completely understood. Their origin, whether they represent a distinct mode of convection from the granules or simply larger versions of the same phenomenon, is an active area of solar research. The Inouye Solar Telescope and the Solar Orbiter spacecraft, a joint ESA-NASA mission, launched in 2020, that is gradually moving into an orbit that will take it closer to the Sun and eventually to higher solar latitudes than any previous spacecraft, are both providing new data on solar convection. The Solar Orbiter is a particularly notable mission because it is designed to observe the Sun's polar regions, which have never been well observed because Earth and all previous solar spacecraft have been confined to the plane of the solar system, which views the Sun's equator but not its poles. The poles are important because they are where the Sun's magnetic field lines converge and where the solar wind originates most cleanly. Observing the poles will help answer fundamental questions about the solar dynamo and the origins of the solar cycle. The convection zone creates the roiling, bubbling surface appearance that the Sun has when observed closely. The entire surface of the Sun is covered in these granules, perhaps 2 million of them at any given time, each rising and falling in the ceaseless convective motion that carries energy from the radiative zone up to the surface. The surface of the Sun, properly called the photosphere, from the Greek word for light, is the layer we see when we look at the Sun in white light. It's not a solid surface. It's the layer at which the solar plasma becomes thin enough to be transparent to light, so photons can finally escape. It's where the sunlight we receive originates. Its temperature, as I mentioned, is about 5,500 degrees Celsius, and at that temperature, it glows with a yellowish-white light. Now here is something that might surprise you. The color of the Sun is not yellow, it is white, pure white. All the colors of the visible spectrum combined in roughly equal proportions. The Sun appears yellow or orange when viewed near the horizon because Earth's atmosphere scatters blue light more than red light, removing some of the blue from the Sun's spectrum when its light has to travel a long path through the atmosphere at low angles. But the Sun seen from space, or high in a clear sky, is white. Astronauts on the International Space Station, asked to describe the color of the Sun, say white, almost painfully bright white. The photosphere has a number of striking features, visible through a telescope, the most famous of which are sunspots. But before we discuss sunspots, I want to say something about solar eclipses, because they have played a unique and remarkable role in the history of solar science, and they're one of the most extraordinary experiences available to any human being. A total solar eclipse occurs when the moon passes directly between the Earth and the Sun, blocking the Sun's disk completely. Total solar eclipses are possible because of a remarkable coincidence. The Sun is about 400 times larger in diameter than the Moon, but the Sun is also about 400 times further away from Earth. these two factors cancel out, so that the sun and the moon appear nearly the same size in the sky. When the moon passes in front of the sun, it fits almost perfectly over the solar disk. Not exactly, because the moon's orbit is not perfectly circular and the Earth-moon distance varies, but closely enough that for observers in the narrow path of totality, the moon briefly covers the sun completely. During totality, the bright photosphere is hidden and the corona becomes visible for the first time. Without totality, the corona is simply too faint to see against the brightness of the sky surrounding the sun. But during the few minutes of totality, the corona blazes into view, a pearly white halo extending several solar radii around the moon's silhouette. It is, by all accounts, one of the most extraordinary spectacles in nature. People who have seen a total solar eclipse often say it changed them. They describe a profound and almost overwhelming sense of the solar system as a real three-dimensional place, with the moon, a real solid ball, casting a real shadow on the real Earth. Total solar eclipses have been scientifically crucial. The chromosphere and corona were first systematically studied during eclipses. Helium was discovered during an eclipse, as we discussed. The test of Einstein's general relativity by Arthur Eddington in 1919 was done during a total solar eclipse. The bending of starlight near the sun could only be measured when the sun's own light was blocked. Modern solar telescopes can create artificial eclipses using devices called coronagraphs, which block the photosphere and allow the corona to be studied outside of natural eclipses. But natural eclipses still provide scientific opportunities, particularly for studying the lower corona, very close to the solar limb, in regions that even the best coronagraphs struggle to observe. And for ordinary human beings, a total solar eclipse is an experience that many describe as one of the most significant of their lives. There is something about standing in the shadow of the moon, watching the sky go dark in the middle of the day, seeing the stars appear, feeling the temperature drop, hearing the birds go quiet, that connects you to the cosmos in an immediate and visceral way that no telescope or photograph can replicate. The universe suddenly feels real, present, physical, in a way that ordinary daily life rarely allows. The next total solar eclipses visible from various parts of the world are predictable centuries in advance. If you haven't seen one, and you get the chance, consider making the effort. It's worth it. The photosphere has a number of striking features, visible through a telescope, the most famous of which are sunspots. Sunspots are dark regions on the sun's surface, ranging from small features a few hundred kilometers across to enormous structures that can span more than 100,000 kilometers, larger than Earth. They appear dark not because they're truly dark, but because they're cooler than the surrounding photosphere. A sunspot might be at a temperature of about 3,500 to 4,500 degrees Celsius, compared to the surrounding 5,500 degrees. That cooler region emits less light and therefore appears darker in contrast. If a sunspot could be isolated from the sun and observed alone, it would still be brighter than the full moon. Sunspots are caused by intense concentrations of the sun's magnetic field. The magnetic field in a sunspot is so strong, perhaps 3,000 times stronger than Earth's magnetic field, that it suppresses the convective motion that normally carries heat from below to the surface. Without convection to deliver heat, the region cools down, forming the dark spot. Sunspots are not isolated phenomena. They are associated with intense magnetic activity that can produce a wide range of solar events. Solar flares are sudden, explosive releases of energy from regions near sunspots, producing intense bursts of radiation across the electromagnetic spectrum, from radio waves to X-rays to gamma rays. Coronal mass ejections are enormous eruptions of plasma from the sun's surface, hurling billions of tons of solar material into space at millions of kilometers per hour. And solar prominences are huge arching structures of dense plasma held in place by magnetic fields, sometimes spanning hundreds of thousands of kilometers above the surface, like enormous glowing bridges or loops. All of these phenomena are driven by the sun's magnetic field, and understanding them requires understanding something about solar magnetism. The sun's magnetic field is generated deep within it, in the region where the radiative zone meets the convection zone, a boundary layer called the tachocline. At the tachocline, the slower, solid body-like rotation of the radiative zone meets the differential rotation of the convection zone, where different latitudes rotate at different speeds. The sun does not rotate like a rigid ball. The equatorial regions rotate faster than the polar regions. The equator completes a rotation in about 25 days, while the poles take about 35 days. This differential rotation, combined with the convective motion, generates and amplifies magnetic fields through a process called the solar dynamo. The solar dynamo is not perfectly understood, even today. The details of how convection and differential rotation combine to produce the complex, evolving magnetic patterns we observe are still being worked out. It is one of the active research areas in solar physics because the behavior of the sun's magnetic field has real consequences for Earth through what's called space weather. Space weather refers to the effects of solar activity on Earth's near-space environment and, indirectly, on the surface. When a coronal mass ejection reaches Earth, typically 1 to 3 days after the eruption, it can compress Earth's magnetic field, sending charged particles streaming into the upper atmosphere. At the poles, where Earth's magnetic field lines converge and particles can penetrate deeper into the atmosphere, these particles collide with oxygen and nitrogen atoms and excite them, producing the auroras. The northern lights and the southern lights are, at their heart, the visible signature of the sun reaching out and touching our planet's atmosphere. At their most intense, solar storms can do more than produce auroras. The massive solar storm of 1859, known as the Carrington Event, was the most powerful solar storm ever recorded. It produced auroras visible as far south as Cuba and the Hawaiian Islands, which are at tropical latitudes. It caused severe disruptions to telegraph systems across North America and Europe. Telegraph operators reported electric sparks flying from their equipment. Some lines continued to transmit messages even after the operators disconnected the batteries, powered by the induced currents from the solar storm. The Carrington event was so severe that if a comparable storm happened today, it would potentially cause trillions of dollars of damage to electrical infrastructure, satellite systems, and communication networks. We've come to depend so deeply on the sun's relative calm, on its steady output and the absence of extreme events, that we rarely think about what happens when it's not calm. But the sun is not always calm. It cycles through periods of higher and lower magnetic activity on an approximately 11-year cycle, called the solar cycle. During solar maximum, sunspots are numerous, solar flares are frequent, coronal mass ejections are more common. During solar minimum, the sun is quieter. We're currently in an active phase of solar cycle 25, which began around December 2019. The solar cycle has been observed and recorded for about 200 years, since astronomers began systematically counting sunspots. Before that, we have records going back further through the observation of auroras, which are more common and extend to lower latitudes during solar maxima. And we have a remarkable natural archive of past solar activity, encoded in the isotopes of certain elements, particularly carbon-14 and beryllium-10, found in ice cores and tree rings. When cosmic rays, whose flux at Earth is modulated by the solar wind, produce these isotopes in the upper atmosphere, they eventually get deposited in ice or incorporated into tree rings. By measuring the concentrations of these isotopes at different depths in ice cores or in different tree rings, scientists can reconstruct the history of solar activity going back thousands of years. This archive has revealed some fascinating features. There have been periods in historical times when solar activity was much lower than it is today. The most famous of these is the Maunder Minimum, a period from about 1645 to 1715, when sunspots were extremely rare. During the Maunder Minimum, only about 50 sunspots were observed in a 70-year period, compared to the 40 to 50,000 that would be expected during normal conditions. This period coincides with the coldest part of what is known as the Little Ice Age in Europe, though the relationship between solar activity and climate is complex, and the sun's contribution to the Little Ice Age has been debated. Most climate scientists think the solar contribution was a relatively minor factor compared to volcanic activity and other forcings. But it's clear that solar activity can vary significantly over centuries, and we don't fully understand all the driving mechanisms. The most intense solar storm ever recorded in the modern era was the Carrington Event of September 1859, named after the British astronomer Richard Carrington, who observed the solar flare that triggered it. Carrington was watching the sun through a telescope on the morning of September 1st, 1859, and he saw a sudden, intense brightening in a sunspot group, a white light flare, the first solar flare ever directly observed. He was excited enough to rush out to call a witness, and by the time he returned, the flare had begun to fade. Approximately 17 hours later, a remarkable thing happened worldwide. Auroras were visible as far south as Colombia, Cuba, Hawaii, and Queensland, Australia. In some places, the auroras were so bright that people woke up thinking it was dawn. The lights were red, green, and white, filling the entire sky. In the Rocky Mountains, gold miners woke up and began making breakfast, thinking the sun had risen. Simultaneously, telegraph systems across North America and Europe went haywire. Operators reported intense sparks flying from their equipment. Some systems caught fire. Many lines simply refused to transmit. But the most extraordinary phenomenon was that some telegraph systems kept working, even when operators disconnected the batteries, powered entirely by the induced electrical currents from the storm. Operators were able to send and receive messages without any power source at all, using only the current the solar storm was inducing in the lines. If a Carrington-scale event happened today, the effects would be catastrophic. Satellites, which are extremely vulnerable to intense radiation and particle flux, could be damaged or destroyed. The global positioning system could fail. Radio communications would be severely disrupted. Power grids, particularly long-distance high-voltage transmission lines, which act as enormous antennas for geomagnetically induced currents, could experience widespread transformer failures. Modern power transformers are expensive, custom-built, and take months to years to manufacture. If large numbers of them failed simultaneously, some regions could face power outages lasting months or even years. The vulnerability of modern civilization to extreme solar events is a serious concern in the space weather community. Space agencies and national meteorological services now operate space weather forecasting centers, trying to predict dangerous solar events. The main forecasting facility for the United States is the Space Weather Prediction Center in Boulder, Colorado, operated by NOAA. Similar centers operate in Europe and elsewhere. The Parker Solar Probe and other solar observatories provide data that allows forecasters to give some warning, typically 15 minutes to a few hours, before a solar storm hits Earth. We're currently in an active phase of solar cycle 25, which began around December 2019 and is tracking as more active than the previous cycle. Solar maximum was expected to occur around 2025, and observations through 2024 suggested the cycle was more active than predicted. The Sun is, right now in the late 2020s, somewhat more stormy than average. Solar flares and coronal mass ejections have been occurring with elevated frequency. The auroras have been visible at unusually low latitudes. None of this is dangerous, but it's a reminder that the Sun is a dynamic, active star, not simply a steady lamp in the sky. Let me now take you above the Sun's surface, into the atmosphere, because the Sun has an atmosphere, and it is one of the most puzzling places in the solar system. But first, let me tell you about one of the most remarkable scientific developments in solar physics of the last few decades: helioseismology. Helioseismology is the study of the Sun's interior through the analysis of acoustic oscillations, sound waves, that propagate through the Sun's interior and produce very small but measurable motions on the surface. The Sun rings like a bell, though at frequencies far below what human ears can detect. These oscillations are driven by the turbulent convection near the surface, which constantly disturbs the Sun and excites waves at many different frequencies. By carefully analyzing the spectrum of these oscillations, the way the frequencies depend on the depth and direction of propagation, helioseismologists can infer the properties of the Sun's interior, much the way seismologists use earthquake waves to probe Earth's interior. The technique has been extraordinarily powerful. It has allowed us to measure the rotation rate of the Sun at different depths, revealing the differential rotation and the tachocline, where it changes character. It has revealed the depth of the convection zone. It has provided constraints on the temperature and chemical composition of the Sun's interior that can be compared to theoretical models. In fact, helioseismology played a crucial role in the solar neutrino story. When Ray Davis's neutrino detector was showing only a third of the expected neutrinos, the solar models were scrutinized intensely for possible errors. Helioseismology showed that the models of the solar interior were extremely accurate, matching the observed oscillation frequencies with remarkable precision. The solar model was right. The discrepancy had to be in the neutrinos, not the Sun. Helioseismology helped establish the case for neutrino oscillations. The SOHO spacecraft, the Solar and Heliospheric Observatory, a joint mission of NASA and the European Space Agency, launched in 1995 and still operating, carries instruments specifically designed for helioseismology, alongside instruments for studying the solar corona, solar wind, and other aspects of the Sun. SOHO has monitored the Sun continuously for nearly 3 decades, providing an unprecedented record of solar behavior and enormously advancing our understanding of the solar interior and dynamics. Another recent development in solar observation is the Daniel K. Inouye Solar Telescope in Hawaii, completed in 2022. It is the largest solar telescope in the world, with a 4-meter primary mirror. Its early images of the Sun's surface showed the granulation pattern in more detail than ever before, with individual granules resolved down to scales of about 30 kilometers. It also showed structures within sunspot magnetic fields that had not previously been visible. The Inouye telescope is expected to revolutionize our understanding of solar magnetism and the coronal heating problem over the coming decades. Let me now take you above the sun's surface, into the atmosphere, because the sun has an atmosphere, and it is one of the most puzzling places in the solar system. The first layer above the photosphere is the chromosphere, from the Greek word for color. The chromosphere extends for about 2,000 kilometers above the photosphere. Its temperature rises from about 4,000 degrees at the bottom, where it meets the photosphere, to about 25,000 degrees at the top. Already something strange is happening. Temperature is increasing as you move away from the sun's surface, which is the opposite of what you'd expect. As you move away from a heat source, you normally expect it to get cooler, not hotter. This temperature inversion is one of the earliest hints of a larger mystery. Above the chromosphere is a thin transition region where the temperature rockets upward from 25,000 degrees to over 1,000,000 degrees in a distance of only a few hundred kilometers. And then you enter the corona, the sun's outermost atmosphere, which extends millions of kilometers into space and is at a temperature of 1 to 3 million degrees Celsius. The corona is 1,000,000 degrees. The surface of the sun is 5,500 degrees. The sun's atmosphere is almost 200 times hotter than its surface. This is the coronal heating problem, and it is one of the great unsolved problems in solar physics. The energy for heating the corona must ultimately come from the sun's interior. But how? The sun radiates energy outward. Moving outward from the core, you generally go from hotter to cooler. The core is 15 million degrees. The radiative zone is somewhere in between. The surface is 5,500 degrees. That's the natural gradient. So why is the outermost atmosphere at 1,000,000 degrees? Several mechanisms have been proposed. One is wave heating. The convective motion in the sun's surface creates waves that propagate along magnetic field lines into the corona, depositing energy as they travel. Another is magnetic reconnection heating. The complex, tangled magnetic fields in the corona can snap and reconnect in new configurations, releasing energy explosively. A third, related mechanism is nanoflares, proposed by the solar physicist Eugene Parker. Parker suggested that the corona is heated by a vast number of tiny, frequent reconnection events, each too small to observe individually, collectively keeping the corona hot. The Parker Solar Probe, a NASA spacecraft launched in 2018 and named after Eugene Parker, is designed to help answer this question. It's the first spacecraft to fly through the solar corona, passing closer to the sun than any human-made object has ever been, skimming to within about 6 million kilometers of the sun's surface, well inside the orbit of Mercury. At that distance, it experiences intense heat and radiation, protected by a carbon composite heat shield. It has been making close passes to the sun, getting closer on each orbit, and sending back data about the plasma and magnetic fields of the inner solar corona. The data it's returning is providing new insights into the physics of the corona and may eventually help resolve the coronal heating mystery. The corona is also the source of the solar wind, a continuous stream of charged particles, mostly protons and electrons, that flows outward from the sun in all directions at speeds of 300 to 800 kilometers per second. The solar wind pervades the entire solar system. It flows past all the planets, past the comets, past Pluto, past the outer reaches of the solar system, and eventually, at a boundary called the heliopause, it meets the interstellar medium and stops. The Voyager probes, launched in 1977 and still operating, crossed the heliopause in 2012 and 2018, becoming the first human-made objects to enter interstellar space. Even at their immense distances of more than 20 billion kilometers from the Sun, they had been traveling through solar wind for their entire journey. The Parker Solar Probe deserves more than a mention because it represents one of the most audacious engineering achievements in the history of space exploration. The spacecraft has to withstand temperatures of about 1400 degrees Celsius on its sunward-facing heat shield, while keeping its instruments at room temperature on the other side of the shield. The heat shield is made of a carbon composite material, 8 feet in diameter and about 4.5 inches thick, that has extraordinarily low thermal conductivity, keeping the spacecraft's body cool while the shield itself glows with the heat of the corona. The mission was conceived decades before it became technically feasible, first proposed in the 1990s. The engineering challenges were formidable. At the distances the probe flies past the Sun, solar radiation pressure is intense enough to significantly affect the spacecraft's trajectory. The probe has to operate autonomously during its closest passes to the Sun, because the communication delay with Earth is too long for real-time control. The thermal system has to be extremely reliable, because any failure that exposed the spacecraft's instruments to direct sunlight at that distance would be catastrophic and immediate. Eugene Parker, the physicist for whom the probe is named, proposed the existence of the solar wind in 1958 in a paper that was famously rejected by 2 referees before it was finally published. The reviewers didn't believe the Sun could be producing a continuous stream of particles in the way Parker described. The solar wind was confirmed observationally by the Soviet Luna 1 mission in 1959 and by later observations, vindicating Parker completely. The naming of the Parker Solar Probe in his honor was announced in 2017, while Parker was still alive at age 90. He attended the launch in 2018. He died in 2022 at the age of 94, having seen his ideas about the solar wind confirmed and explored in extraordinary detail. The data from the Parker Solar Probe has already produced important results. It has found that the magnetic field near the Sun is more complex and variable than expected, with frequent reversals, called switchbacks, that appear to be related to energy transport mechanisms. It has provided evidence for dust-free zones very close to the Sun, where intense sunlight vaporizes dust particles. It has measured the solar wind at distances never reached before, providing constraints on the acceleration mechanisms that drive it to the high speeds observed at Earth's distance. It has made progress on the coronal heating problem, though the final answer is not yet in hand. The several mechanisms proposed for coronal heating are still being evaluated against the Parker Solar Probe data. Wave heating, magnetic reconnection, nanoflares, or some combination of these may all contribute. The heating of the corona remains one of the most active research areas in solar physics, and the answer, when it comes, will likely require data from the Parker Solar Probe's closest passes to the Sun, which were still being performed as of 2024. The solar wind has profound effects on planets. Planets with strong magnetic fields, like Earth, deflect most of the solar wind, though some particles penetrate to produce auroras. Planets without magnetic fields, like Mars and Venus, have their atmospheres directly sculpted by the solar wind. Mars, which lost its magnetic field billions of years ago, has had much of its atmosphere stripped away by the solar wind over geological time, contributing to its current thin atmosphere and cold, dry surface. The role of the solar wind in shaping planetary atmospheres is one of the active areas of planetary science, studied by missions like MAVEN, which orbited Mars specifically to study the solar wind's effect on Martian atmospheric escape. Now, let me tell you something about the Sun that I find quietly astonishing, even having known it for years. The sun is mostly hydrogen. About 71% by mass is hydrogen, and about 27% is helium. Everything else, all the heavier elements, carbon, nitrogen, oxygen, iron, gold, all of it, makes up only about 2% of the sun's mass. 2%. The universe is overwhelmingly made of the simplest, lightest elements, and the sun is a typical sample of the universe. We know the composition of the sun because of spectroscopy, the study of how different elements absorb and emit light at specific wavelengths. When sunlight passes through a prism or a spectroscope, it spreads into a rainbow of colors, but the rainbow is crossed by dark lines, specific wavelengths where the light has been absorbed. These are the Fraunhofer lines, first systematically studied by the German physicist Joseph von Fraunhofer in the early 19th century. Joseph von Fraunhofer had an extraordinary and poignant life. He was born in Bavaria in 1787, the youngest of 11 children of a glazier, a maker of window glass. Both of his parents died before he was 12, leaving him an orphan who was apprenticed to a glassmaker in Munich. In 1801, when he was 14 years old, the building where he worked collapsed, killing or injuring everyone else present. Fraunhofer was pulled from the rubble alive. The Elector of Bavaria, Max Joseph, who happened to be visiting the disaster scene, took a personal interest in the boy and gave him money to use as he saw fit. Fraunhofer used the money to buy books and time off to study. He taught himself mathematics and optics. He became one of the most skilled optical instrument makers in Europe, developing new methods for producing glass of extraordinary quality and uniformity. The optical instruments he made were the finest available anywhere in the world, and he supplied them to observatories and scientific institutions across the continent. In 1814, using an exceptionally good prism and a narrow slit to allow a thin beam of sunlight to enter his spectroscope, Fraunhofer observed the absorption lines in the solar spectrum that now bear his name. He mapped over 500 of them, labeling the most prominent ones with letters that are still used today. The D lines, the two close yellow lines, are still called the sodium D lines. The B and A lines in the red, the C line in the deep red, the G lines in the blue-green, all named by Fraunhofer. He didn't fully understand what caused the lines. He observed that some lines appeared in the spectra of other stars and the moon, and that some didn't, suggesting the lines carried information about the composition of the sources. He died in 1826, at the age of 39, probably of tuberculosis, before the theory of spectral lines was worked out. The understanding of what the Fraunhofer lines meant came over the next several decades, through the work of Gustav Kirchhoff and Robert Bunsen in Heidelberg in the late 1850s. Kirchhoff showed that each element had a characteristic pattern of absorption and emission lines, that a cool gas absorbed exactly the wavelengths that a hot gas of the same composition emitted, and that the dark lines in the solar spectrum were produced by absorption in the cooler outer layers of the sun. Bunsen, whose name is attached to the laboratory gas burner he helped develop, collaborated with Kirchhoff in matching the solar spectral lines to the lines of known elements, identifying sodium, iron, calcium, magnesium, and others in the sun. Each element has a characteristic pattern of absorption lines, like a fingerprint in light, and by matching the patterns in the sun's spectrum to the patterns of known elements, chemists and physicists have been able to determine exactly what the sun is made of. The French philosopher Auguste Comte, in the 1830s, listed the chemical composition of stars as a prime example of knowledge that humanity could never hope to attain. Stars were simply too far away, too inaccessible, to ever yield their secrets to analysis. Within a generation, spectroscopy had proved him completely wrong. It's one of the most famous examples of a confident prediction about the limits of science being overturned almost immediately. The discovery of helium is particularly telling. During a solar eclipse in India on August 18, 1868, the French astronomer Jules Janssen set up a spectroscope to observe the chromosphere, the thin layer of the solar atmosphere just above the surface, which is normally invisible but can be seen during eclipses when the moon blocks the bright photosphere. Janssen saw a bright yellow line in the spectrum. He initially thought it was the sodium D line, but a few months later, the English astronomer Joseph Norman Lockyer, who had not been present at the eclipse, but had independently been developing techniques for observing the chromosphere without an eclipse, also saw the yellow line and showed that it was very slightly offset from the sodium D lines. It was not sodium. Lockyer concluded that it must be an unknown element. He named it helium, after Helios, the Greek sun god. The name was given to an element that existed, as far as anyone knew, only in the sun, detected by light that had traveled 93 million miles to a spectroscope in England. In 1882, the Italian astronomer Luigi Palmieri detected what he thought might be helium in volcanic gases from Mount Vesuvius, but the identification wasn't certain. The definitive discovery of helium on Earth came in 1895, when the Scottish chemist William Ramsay was heating uranium-bearing mineral cleveite in acid and collecting the gas released. He sent a sample to Lockyer, who confirmed that the spectrum matched helium. An element discovered in the Sun in 1868 had been found on Earth 27 years later. Helium is, as it turns out, the second most abundant element in the universe, making up about a quarter of all ordinary matter by mass, but it's relatively rare on Earth because it's too light to be held by Earth's gravity and escapes into space. The helium in party balloons ultimately comes from natural gas wells, where it has accumulated over geological time as the decay product of uranium and thorium. It is, in that sense, a non-renewable resource, extracted once and released forever. The story of helium captures something beautiful about science. An observation of light from a star led to the identification of an element, which eventually turned out to be one of the most fundamental substances in the universe, the ash of stellar fusion, the second most abundant element in existence, present in every star, found on Earth only as a trace gas from radioactive decay. One spectral line in a solar eclipse led to all of this. Now let me talk about the future of the Sun, because the story of how the Sun works is incomplete without the story of how it ends. And the ending, while ultimately devastating for everything alive on Earth, is also in its own way extraordinary. The Sun is about 4.5 billion years old. It was formed about 4.5 billion years ago from a collapsing cloud of gas and dust, in a process we've described in our conversation about neutron stars. It has been fusing hydrogen in its core ever since, steadily converting mass to energy, gradually increasing in luminosity. And it is a fact that the Sun is not exactly the same as it was when it formed. It has been very slowly getting brighter over its lifetime. In its first billion years, it was about 70% as bright as it is today. This creates an interesting puzzle in the history of Earth. If the early Sun was significantly fainter, simple calculations suggest that Earth should have been frozen solid for most of its early history, since the energy from the Sun was insufficient to keep water liquid. Yet geological evidence shows that Earth's oceans were liquid very early, Life was beginning in the first billion years, and the planet was clearly habitable. This contradiction is called the faint young sun paradox, and it has not been fully resolved, though various explanations have been proposed. The early Earth may have had much higher concentrations of greenhouse gases, particularly carbon dioxide and methane, that provided enough warming to compensate for the fainter sun. Or the early Earth may have been more covered with land surfaces that absorbed more of the sun's radiation than today's ocean-dominated surface. Or there may have been other factors we haven't fully accounted for. The paradox is one of the active puzzles in the history of Earth's climate. Over the next 5 billion years or so, the sun will continue to brighten. In about 1 billion years, it will be about 10% brighter than today. That doesn't sound like much, but climate models suggest it may be enough to trigger a runaway greenhouse effect on Earth. As the sun brightens, more water evaporates. Water vapor is a potent greenhouse gas, which causes more warming, which causes more evaporation, in a positive feedback loop that eventually boils off the oceans. Earth may become uninhabitable for complex life in 1 billion years, even though the sun will still be a main sequence star for another 4 billion years after that. This is a sobering thought, and one that puts human civilization in a somewhat different perspective. On cosmological timescales, we are not early in the Earth's habitable lifetime. We are about 4.5 billion years into a roughly 5.5 billion year habitable window. The Earth has about 1 billion years left as a comfortable home for complex life, assuming nothing else interferes. 1 billion years is still an almost incomprehensible amount of time, and humanity may not survive anything like that long for a dozen different reasons. But it's worth knowing that even the steady shining of the sun is not forever. In about 5 billion years, the sun will exhaust the hydrogen fuel in its core. When the hydrogen in the core runs out, the core will contract and heat up. Hydrogen fusion will continue in a shell around the core, releasing more energy than before. The extra energy will cause the outer layers of the sun to expand enormously. The sun will become a red giant. The red giant phase is one of the most dramatic transformations in stellar evolution. The sun, which is currently a fairly average-sized yellow star, will expand to perhaps 100 to 200 times its current radius. As it expands, its surface temperature will drop, which is why the surface will appear red or orange rather than yellow. The luminosity will increase enormously despite the lower surface temperature, because the increased surface area more than compensates for the lower temperature per unit area. During the red giant phase, the sun's outer layers will extend to regions that are currently the inner solar system. Mercury and Venus will almost certainly be engulfed and vaporized. Earth's fate is more uncertain. Models vary in their predictions, depending on how much mass the sun loses during the expansion, because mass loss changes the gravitational dynamics. Some models suggest Earth will be engulfed. Others suggest it will spiral outward as the sun loses mass. Either way, any surface life on Earth will have been incinerated long before this point, as the sun's brightening over the intervening billions of years makes the surface uninhabitable. The engulfment is a final punctuation mark, not the story. During the red giant phase, hydrogen shell burning will eventually ignite helium fusion in the core. Helium fusion, through the triple alpha process we described when discussing neutron stars, converts helium to carbon and oxygen, releasing energy. The onset of helium fusion in the red giant core happens through a dramatic event called the helium flash. Because the core of a red giant is a degenerate electron gas, meaning its pressure is determined by quantum mechanical effects rather than temperature, the ignition of helium fusion doesn't happen smoothly. Instead, When helium fusion begins, the energy release doesn't immediately cause the core to expand and cool. The degenerate core can't expand in the normal way in response to heating, so the fusion accelerates, heating the core further, accelerating the fusion more, in a runaway event called the helium flash that releases enormous energy in a very short time. The helium flash is not directly observable because it takes place deep inside the star, but models suggest it releases as much energy in a few seconds as the sun emits in millions of years, all of it immediately absorbed by the star's outer layers. After the helium flash, the core returns to non-degenerate behavior. Helium fusion stabilizes, and the sun settles into a second stable phase called the horizontal branch. In this phase, it fuses helium in its core and hydrogen in a surrounding shell, and it's somewhat smaller and hotter than it was during the red giant phase. This second stable phase is shorter than the main sequence phase, but lasts for tens to hundreds of millions of years. When the helium in the core runs out, the sun again forms an inert core, this time of carbon and oxygen, with helium and hydrogen burning in shells around it. The star expands again into an even larger red giant, called an asymptotic giant branch star. The luminosity pulsates. The outer layers become increasingly unstable. Strong stellar winds begin blowing material off the surface. During this asymptotic giant branch phase, the sun will shed its outer layers in a series of pulsations and stellar wind episodes, blowing them gently off into space over hundreds of thousands of years. The shed material will form a beautiful, expanding shell of gas around the star, illuminated by the ultraviolet radiation from the hot core left behind. This is a planetary nebula, one of the most visually stunning objects in the universe. Planetary nebulae have nothing to do with planets, despite their name. The name comes from 18th and 19th century astronomers, who, looking at them through early telescopes, thought they resembled the disks of planets. They are now understood to be the final exhalations of sun-like stars that have completed their hydrogen and helium burning and released their outer layers into space. Some of the most iconic astronomical images ever taken are of planetary nebulae. The Ring Nebula in Lyra, which looks like a glowing ring of bluish-green gas with a central white star, is a planetary nebula visible through a small telescope. The Helix Nebula in Aquarius, sometimes called the Eye of God because of its appearance in images from space telescopes, is one of the largest and closest planetary nebulae to Earth. The Cat's Eye Nebula, the Butterfly Nebula, the Boomerang Nebula, each is a dying star of roughly solar mass, caught in the act of releasing its outer layers into space. The material released in a planetary nebula doesn't disappear. It drifts into the surrounding interstellar medium, cooling and eventually being incorporated into new gas clouds that will eventually collapse to form new stars and solar systems. The carbon and oxygen in the sun's core, synthesized over billions of years of stellar fusion, will be dispersed into the galaxy and will eventually become part of new worlds, new planets, potentially new living things. The atoms of the sun will not be lost. They will be recycled. What's left behind after the sun sheds its outer layers will be a white dwarf. A white dwarf is the exposed core of a dead star, about the size of Earth but with about the mass of the sun. It is extraordinarily dense. A teaspoon of white dwarf material would weigh about 15 tons. The white dwarf is not fusing anything. It's supported not by pressure from nuclear reactions, but by the quantum mechanical pressure of electrons, called electron degeneracy pressure. the same effect that keeps electrons from being compressed together in ordinary matter. A white dwarf shines with a white-hot light at first, fed by the residual heat from its formation. It has no internal energy source, so it can only cool. Gradually, over billions of years, it cools, from white to yellow to orange to red, becoming dimmer and dimmer. Eventually, after tens of billions of years, it would cool completely and become a black dwarf, an invisible cold sphere of carbon and oxygen drifting in the dark. But as I mentioned in our neutron star conversation, the universe is not old enough for any white dwarfs to have cooled to black dwarfs yet. The oldest white dwarfs, formed from the first generation of stars that lived and died in the first billion years of the universe, are still cooling. They've had 13 billion years to cool and are still dim red objects. True black dwarfs, if they exist, lie in the future. The Sun's ultimate fate, a slowly cooling white dwarf, surrounded by the beautiful nebula of its shed outer layers, is a gentle ending for a medium-sized star. It won't explode as a supernova. It's not massive enough for that. It will just bloom briefly into a red giant, scatter its outer layers, and leave a glowing remnant to cool in the dark. But that is 5 billion years away. We have time. Right now, tonight, the Sun is doing what it has been doing for 4.5 billion years, fusing hydrogen in its core, converting 4 million tons per second of mass to energy, radiating that energy through 100,000 years of random walk through the radiative zone, then convecting it upward through the convection zone, releasing it from the photosphere as the warmth and light that reaches Earth 8 minutes later. And that light, when it reaches Earth, does something extraordinary. It powers life. Photosynthesis is the process by which plants, algae, and some bacteria capture the energy of sunlight and use it to convert carbon dioxide and water into glucose and oxygen. It is the most important chemical reaction on Earth. Without it, there would be no oxygen in the atmosphere. There would be no food for animals. There would be no forests, no grasslands, no coral reefs, no ecosystems of any complexity. The entire web of life on Earth is built on photosynthesis, which is built on sunlight. The elegance of photosynthesis is remarkable. A plant absorbs a photon of light that originated in the sun's core 100,000 years ago. The energy of that photon is used to drive a series of chemical reactions that split water molecules, releasing oxygen as a byproduct, and combine the hydrogen with carbon dioxide to produce glucose. The glucose is then used as fuel for the plant's metabolism, as building material for growth, as energy that can be passed along to any animal that eats the plant. Every calorie you've ever consumed ultimately came from a photon that left the sun's core 100,000 years ago. Every molecule of oxygen you've ever breathed was released by photosynthesis, powered by ancient sunlight. The food web, the oxygen cycle, the carbon cycle, the water cycle, as driven by solar evaporation, all of it is running on the sun's output. This connection between the sun and life is not metaphorical. It is literal and biochemical. The ATP molecule that powers your muscles and your neurons and every other energy-requiring process in your body was ultimately made from solar energy, passed through photosynthesis and up the food chain. The warmth of your body is solar energy, transformed through chemistry into heat. You are, in the most direct physical sense, a solar-powered organism. Now, the sun doesn't shine only in the visible wavelengths that photosynthesis uses. It radiates across the entire electromagnetic spectrum, from radio waves to gamma rays. Some of that radiation is beneficial. The ultraviolet radiation from the sun causes your skin to synthesize vitamin D, which is essential for bone health and immune function. Some of it is harmful. Intense ultraviolet radiation can damage DNA and cause skin cancer, which is why Earth's ozone layer, which blocks most ultraviolet radiation, is so important for life on the surface. Infrared radiation from the sun warms Earth's surface and drives the weather patterns. X-rays and extreme ultraviolet radiation from the corona heat Earth's upper atmosphere and influence its ionosphere, the electrically charged layer that affects radio communications. The full electromagnetic output of the sun shapes Earth in countless ways, from the visible light that drives photosynthesis and vision, to the infrared that warms the surface, to the ultraviolet that powers vitamin D synthesis and threatens DNA, to the X-rays that are mostly blocked by the upper atmosphere but affect satellite communications, to the solar wind that sculpts the magnetosphere and drives auroras. The sun's influence on Earth is not limited to the warmth on your face. It extends through the entire electromagnetic spectrum and into the charged particle environment of near-Earth space. Right now, tonight, the sun is doing what it has been doing for 4.5 billion years, fusing hydrogen in its core, converting 4 million tons per second of mass to energy, radiating that energy through 100,000 years of random walk through the radiative zone, then convecting it upward through the convection zone, releasing it from the photosphere as the warmth and light that reaches Earth 8 minutes later, that plants capture through photosynthesis, that drives the weather and the seasons, that animals and people have been navigating by, warming themselves by, wondering about, for as long as there have been animals and people to wonder. There's something extraordinary about holding all of that together. The fusion happening in the core right now is creating light that will not reach us for 100,000 years. The light reaching us right now was created 100,000 years ago, before human civilization, before agriculture, before any written word. And yet it feels immediate. It feels present. It falls on your skin and warms you, and the fact that it was created 100,000 years ago by nuclear reactions in conditions we can barely imagine doesn't diminish the warmth at all. Let me say something about what the sun is doing right now, tonight, while you lie in the dark. Because the sun doesn't know it's night. The sun has no experience of night. Night is a feature of being on a rotating planet. From the sun's perspective, it is always shining outward in all directions equally, bathing the entire solar system in its output at all times. The hemisphere of Earth currently facing the sun is experiencing day. The hemisphere facing away is in shadow. But the sun is making no distinction. It's doing the same thing it always does. Right now, as you lie in the dark, the sun is fusing hydrogen at 15 million degrees. It's been doing this continuously, without a moment's pause, for 4.5 billion years. Not once in 4.5 billion years has the fusion in the sun's core faltered. Not once has there been a power cut. Not once has the output wavered in a way that any living thing on Earth has ever noticed. The most reliable process in the history of this planet, running continuously for longer than the Earth has existed, is running right now in the dark while you sleep. There's something deeply calming about that when you let it in. There's something extraordinary about holding all of that together. The fusion happening in the core right now is creating light that will not reach us for 100,000 years. Let me slow all the way down now, and let all of it settle. You've spent some time tonight with the closest star, with the object that makes your life possible, with the engine of the solar system and the driver of almost everything alive on this planet. And what you've learned, slowly, is that it's not fire, not in any sense we normally mean. It's a nuclear furnace so vast and so sustained that it defies the imagination to hold clearly. 4 million tons per second, 15 million degrees at the center, 100,000 years for a photon to reach the surface, 8 minutes to cross the space to Earth. And yet it looks from here like a warm yellow circle, hanging in the blue sky, rising every morning with the dependability that human civilization was built around. Think about that dependability for a moment. Think about what it has meant to every human being who has ever lived. Before electric light, before fire even, the daily rhythm of the sun was the most important fact of existence. When the sun set, darkness came, and darkness was dangerous and cold and disorienting. When the sun rose, you could see, you could move, you could find food and shelter and each other. The sun's rising was so reliable, so utterly without exception over the entire span of human experience, that it became embedded in language and thought as the fundamental metaphor for certainty itself, as sure as the sun rises, as certain as morning. That certainty was not an illusion. It reflected a real fact about the universe. The sun has risen every single day for 4.5 billion years. Not once has it failed to rise. Not once has the nuclear fusion in its core faltered enough to dim its output in any way that life on Earth has ever noticed. The stability of the sun is one of the most extraordinary physical facts in the entire history of the planet. A nuclear furnace 4 times as massive as Jupiter, burning at 15 million degrees, producing the energy of 10 billion hydrogen bombs every second, and doing so with the consistency and precision of a Swiss watch, century after century, billion after billion year. Ancient peoples worshipped the sun because of this reliability, because it was the most dependable thing in existence. The Egyptians had Ra, the sun god, who crossed the sky in a boat during the day and traveled through the underworld at night. The Aztecs had Tonatiuh, for whom human sacrifices were made to ensure the sun would continue to rise. The ancient Irish built Newgrange, a monument older than Stonehenge, aligned so that the rising sun at winter solstice illuminates its inner chamber. The Inca, at Machu Picchu, had the Intihuatana, the hitching post of the sun. Virtually every culture in human history has organized significant religious and ceremonial activity around the sun. These were not superstitions in the simple pejorative sense. They were rational responses to the recognition of something genuinely extraordinary. The people who built these monuments knew, without the physics, that the sun was the source of warmth and light and life, and that its behavior was the single most important fact in their world, and they tried to honor that fact, and perhaps to influence it through ceremony and architecture. The physics we've covered tonight doesn't diminish any of this. It deepens it. When you understand that the sun is a nuclear furnace, sustaining itself through a delicate balance of forces, that its reliability is a consequence of physics that took billions of years and millions of scientists to understand, the ancient reverence seems not primitive but appropriate. The sun is genuinely worthy of reverence. The light reaching you today was created in the sun's core 100,000 years ago. Let that settle in one more time, slowly. 100,000 years ago, early modern humans were spreading across the globe. We had not yet arrived in the Americas. Written language was 100,000 years in the future. The great civilizations of the ancient world were 100,000 years away. The nuclear reactions that produced the photons warming you today happened before any of that, before any city, before any alphabet, before any wheel, before any pottery. The sun was quietly doing its work. And the sun's photons were carrying that energy outward through the plasma, bouncing and being absorbed and re-emitted, slowly, randomly, working their way up through the radiative zone, and then convecting up through the convection zone to the surface, and then 8 minutes across empty space, and then your skin, or the leaves of a tree, or the surface of the ocean, absorbing that ancient energy and turning it into warmth and chemistry and life. Every plant you've ever seen was powered by fusion that happened 100,000 years ago. Every meal you've ever eaten was, at some remove, solar energy from 100,000 years ago. The energy in your body right now, keeping you warm, running your heart, firing the neurons that let you listen to these words, is solar energy from 100,000 years ago that traveled from the core of the sun to the surface and then across space to Earth, and was captured by plants and eaten by something and passed up the food chain to you. You are, in this very immediate and literal sense, a creature of ancient starlight. Tomorrow morning, the sun will rise. The light that hits you tomorrow morning is leaving the sun's core today. In 100,000 years, it will reach the surface. In 100,000 years and 8 minutes, it will hit the Earth. But because the sun has been doing this continuously for 4.5 billion years, there is always light arriving at the surface, always photons making that 8-minute journey, always energy flowing from the core outward through the plasma and across the void to the waiting world. This will continue for another 5 billion years, long after everything any human being has ever built has crumbled to dust, and the dust has been recycled into other things, and the elements have passed through other forms, and the Earth's continents have rearranged themselves, and the oceans have risen and fallen. The sun will still be rising, still fusing hydrogen, still radiating energy, still being, as it has always been, the center of this little solar system, the source of its warmth, the engine of its life. Let that be a comfort tonight. In 5 billion years, the sun will be a red giant, and Earth may be engulfed. But that is so far away as to be irrelevant to any living thing that currently exists, or will exist, or is likely to ever exist on Earth. On all human timescales, the sun is permanent. On all timescales that matter for civilization and for life, the sun is forever. The sun is on the other side of the planet right now. That's why it's dark. It's not gone, just hidden behind the curve of the world. In a few hours, depending on where you are, the Earth will have rotated enough to bring your part of the world back into the light. And the sun will appear again, as it has appeared every single morning for 4.5 billion years, rising with the same reliability that made ancient peoples build monuments to it, that made farmers plant by it, that made sailors navigate by it, that still warms your face every clear afternoon, and still drives every storm, and still powers every photosynthesizing plant. Nothing has changed. The fusion is continuing. The photons are walking their slow, random walk through the plasma. The solar wind is blowing. The corona is glowing at its mysterious 1,000,000 degrees. The granules are rising and falling on the photosphere. The sunspots are spinning with the sun's rotation, marking the places where the magnetic field is especially concentrated. The Parker Solar Probe is orbiting, gathering data, sending information back to Earth at the speed of light, 8 minutes later than when it was sent. All of it, all the time, continuously, without pause, for 4.5 billion years. The sun doesn't know you're sleeping. It doesn't notice the night. For the sun, there is no day or night. Only the continuous nuclear fire at the center and the continuous flow of energy outward, into space, in all directions, available to whatever worlds are in the right places to receive it. Earth is in the right place. You are on Earth. This is not a small thing. Let your breathing slow. Let the images drift. The granules on the sun's surface, rising and falling in their 10-minute cycles, replacing themselves, always new, always the same. The sunspots, dark and cool and magnetized, evolving over days and weeks. The corona, glowing at its mysterious 1,000,000 degrees, its heating mechanism still not fully understood, still puzzling the scientists who study it. The solar wind, streaming outward, filling the solar system with charged particles, making the auroras at the poles, shaping the atmospheres of planets, reaching all the way to the boundary with interstellar space. The sun, doing what it does, as it has always done, as it will do, for as long as anything on Earth exists to receive it. Let your body be heavy. Let the warmth you felt today, if you felt any, be the last thing in your mind before you sleep. That warmth was nuclear fire from 100,000 years ago. That warmth was fusion at 15 million degrees. That warmth was a photon that started its journey before your ancestors' ancestors' ancestors were born, and it reached you today, and it warmed your skin. That is extraordinary. That is the sun. Sleep well. The sun is on the other side of the world. It will be back in the morning. It always comes back. Rest well. The fusion is continuing. The photons are walking. The energy is flowing. Everything is as it should be. Sleep well.